Hello. This is a video on arithmetic and geometric series. Let's begin with defining what we mean by a series. First of all, the term sequence, which we had previously in the course, we had a arithmetic sequence and a geometric sequence. For example, let's say we have 11, 16, 21, and so on. This is an example of an arithmetic sequence. It's a function, and there's a common difference. A series is simply the sum of the terms. So we have 11 plus 16 plus 21, and typically it's going to be finite. I think what I'm going to do here is I'm going to go up to 31, and I'm going to stop at 31, so we can see a very simple example. Many of the concepts this week are quite easy to grasp. Notationally, they're a little bit messy, but conceptually, they're very easy, quite easy anyway, to understand. And we want to be able to find this series. Well, there's the story of little Freddie Gauss, who in elementary school added up the numbers 1 through 100. In a matter of minutes, to the surprise of his teacher. Maybe I won't tell that whole story here on the video, but we're going to be using what may have been Freddie Gauss's solution. It turns out that if we let this equal S, and we take S but reverse the numbers, 31 plus 26 plus and so on all the way down to 11, and add these two equations, I get 42 and, oh, interesting, 42, 42, 42, and over here we have two copies of our sum. So 2s is equal to 5 times 42, because I have 5 numbers in my series. And if I want s, I simply divide by 2, so we have 5 times 42 divided by 2. So my formula here is that the sum is equal to the number of numbers, times first plus last, divided by 2. This is for an arithmetic series. Let's prove this in general. Okay, I would like to derive the formula for finding the sum of an arithmetic series. Basically, what we're going to do is we're going to do the number example, but we're going to do it in the general case. So let's write down our sum. First term is A1. I'm using the same notation that we used back when we did sequences. My second term is going to be A1 plus 1 copy of D. D is my common difference. My next term is going to be A1 plus 2 copies of D, and so on up through the last term, the nth term, which is A1 plus n minus 1 times D. This is the nth term. And as I did with the numbers, I'm going to make a second copy of my sum, but I'm going to put them in reverse order. So I'm going to put the last term first. Up through A1. I'm going to add these two. So I have 2 copies of my sum. And when I add the columns here, I have 2A1 plus n minus 1 times d plus 2a1 plus n minus 1 times d. I have multiple copies of this, plus finally 2a1 plus n minus 1 times d. Well, how many copies do I have of the 2a1 plus n minus 1 times d? This series has n terms in it, so I have n copies. So 2s is equal to n times 2a1 plus n minus 1 times d. Now, in order to get s, I'm going to divide both sides by 2. My sum is equal to n times, I think what I'm going to do here is I'm going to go ahead and split off the a1 again so that it kind of looks like the first term. a1 plus a1 plus n minus 1 times d divided by 2. This is the formula that we're going to use. The thought bubble on this is n first plus last divided by 2. Now I would like to derive the formula for finding the sum of a geometric series. For example, before we do the derivation, remember what a geometric series is like. It might be 100, and let's say my common ratio is 1/2, so I'm going to have 50. Half of 50 is 25. Half of 25 is 12.5. And half of 12.5, I believe, is 6.25. So let's say we wanted to find this sum. Okay, so what do we do first? We take a special case of the difference of powers. So I'm going to be starting with 1 minus r to the n. Now, ultimately, what we want is the answer to this. a1 plus a1r plus a1r squared plus and so on up through a1r to the n minus 1. This is what we want. So we're going to be building that. So think of this as 1 to the n minus r to the n. From the previous video, this is going to be 1 minus r times, I'm going to have decreasing powers of 1. Well, 1 to any power is 1. And I'm going to have increasing powers of r. So I want 1 plus r squared plus and so on up through r to the n minus 1 power. And you can check this with distributive property. 1 times all these terms gives me 1 plus r squared plus and so on through r to the n minus 1. Negative r times all these terms gives me negative r minus r squared minus r cubed all the way through minus r to the n. And it simplifies to get 1 minus r to the n. If you have questions on that, ask in the discussion area. Now I'm going to divide both sides by 1 minus r. If I divide both sides by 1 minus r, I get 1 minus r to the n over 1 minus r is equal to 1 plus r squared plus and so on up through r to the n minus 1. We're almost getting our geometric series. I just need to multiply through by a1. So in my next line, I'm going to multiply the left-hand side by a1, and I'm going to multiply the right-hand side by a1. And now I can use distributive on the right-hand side, and we have a1 times 1 minus r to the n over 1 minus r is equal to a1 plus a1r plus a1r squared plus up through a1 times r to the n minus 1. And this is our formula for finding a geometric series. Let's apply that to our example. In our example, we have a1 is 100. My common ratio is 1/2, and I have 5 terms. N equals 5. Looks like 775. And 775 divided by 4 is 193.75. Now let's go up and see if that seems reasonable. It does seem reasonable. There's 150, 175, and it's reasonable. Now, I realize the temptation here is to say, well, I'm going to just do this on a calculator. A calculator is a good check doing it this way. However, we want to be able to use the formula and not have to write out all the terms. Okay, I haven't shown too many examples, but we're going to be doing more examples of arithmetic and geometric series in the practice homework, and we will be looking at higher values of n. See you in the next video. Have a great day.